Okay, so we talked about training database, test database, and training algorithm. My next part would focus on a test database. Test database is important, and I want to make a point of it, right? So what usually happens is we have all this data, and I guess if you have ever trained a machine learning algorithm, then you probably already know that what we usually do is we take this data, we split them into two parts. Usually it's 80-20 or 70-30, depends. So the large part is a training database. So we use this data to train our algorithm. And then we use the other part to test the performance of the algorithm, right? So we test, let's say, with the 20% of the data. And then we find, for example, that this is 95% accuracy. The question is, what is this data, right? Do this data really reflect a realistic situation or not? Are these data balanced or not? The quality of the test database is very important for how our algorithm will really perform in reality. So think, for example, also a lot of papers achieving really high accuracies. The question then is, how is the test database? Does it really reflect real situations or not? And that's why it's important to make sure that you have high quality, both training data, of course, because this is going to make your neural network or whatever perform better. But the test database is, ideally, they should come from real situations. Okay? This is not always possible, but just make sure that somehow you keep that in mind. The test database is important. Questions? Yeah.
So my question, so you said we have to divide our data into training and test. Sometimes you need some portion of data for validation throughout the training as well. Is that within the training data set?
I consider that, yeah, part of the training, because then the current algorithm will all take this training data and then do that. And to be honest, the algorithms like TensorFlow will just give the data and they do all the work for you. They're going to split it into training, validation, and test, and they are going to do it for you. Okay. Good. Anybody objects to this takeaway? Have any other? Yeah.
Just about the comment about the frequency of occurrence in real life, where if you're looking at stability of the system, you probably want some more extreme examples in your test data, in your training data set that would happen in real life, like you're not necessarily operating at the edge of stability.
You want them both in your training and your test.
Oh, okay.
Right?
Yeah.
Because you need to train for them as well.
Yeah.
And that's what we're going to discuss a bit as well. Because the motivation there is that in real life, probably you are not going to get these extreme examples because you are never going to be so far out.
Yeah.
And that's where, so his simulated data come in. So create a database that explores the space Yeah.
So qualitatively, you can talk about the quality of data, but quantitatively, how do I assess, is this a good test database, or is this not, or is this set of examples better than this one? Quantitatively, how can you do that?
If there's a way to do that, to assess that?
Assessing what is a good test database.
It's not if you don't try it. So I cannot say that ex ante if this is going to be a good quality database or not. So the way we're going to discuss actually, where we try to focus is on the security boundary. So if we try to map the security boundary correctly, then we think that we have a good quality database because we have all the security boundary, right? And then we figured out that this is not enough. We must also have a balanced data set. So this means that I'm actually going to discuss about this later, but let's discuss it also now, and then again later, then it's going to help, I think, also there. So the real safe operating region is very small compared to the whole unsafe space, right? So what we usually come up with is that we have a lot of data in the unsafe space and very few data in the safe space and a lot in the boundary. The neural network or the decision tree will not train well if the amount of data in the safe space is similar in quantity to the unsafe space. So in that sense, that's a good quality database. It's a balanced data set. Okay. So there are some qualities that we can say ex ante that this looks good or not good, but not, yeah.
Do you just mean evenly distributed?
This can also be positive. For what I meant is equal number of data points, equal number of safe data points to unsafe data points. I didn't say anything about how they are distributed in the space, right? I guess, and let me think it to make sure that, I think evenly distributed is better than, yeah, unevenly in a way.
Because if the space is small and you want equal, then it's not evenly distributed. You know that.
You mean between, no. It's going to be evenly distributed in the safe space and evenly distributed in the unsafe space.
But not with respect to the dimensions.
No. Yeah.
But we have two things. First of all, our system is designed to tolerate, for example, transient stability. So therefore, the data set we create is always unbalanced. The number of the cases where the system goes unstable is less than the number of scenarios where the system remains.
No. If you're going to see the number of eligible operating points, the unsafe region is much larger than the safe region.
Which is output of the AC, right? So you're talking about
AC power flow. So for me, eligible operating points are, for example, every generator can go from Pmin to Pmax. If you take the combination of all Pmin, Pmax, the space is huge compared to the allowable or permissible operating region.
And one more thing, we can use, for example, certification of switches to deal with the imbalance.
Certification like?
So you keep the ratio of label 0 or label 1 in the test and training the same. So
Yeah.
you can deal with the unbalanced data. It's pretty standard.
But first we must be aware that unbalanced data sets create bad algorithms. And then, of course, yes, as you say, we must find good ways to maintain that. Yeah.
So just a
Sure.
comment on
Yeah.
the safe space. Another comment on the safe space versus unsafe space.
Yeah.
If you're training on historical data, then obviously your historical data is biased because your system is not constantly in a state of being unsafe.
I agree. Then if you're taking historical data, you're going to be mostly safe.
Yeah.
But depending also on what you train. But if you train about security assessment, right, you need to explore the whole space. And for that, you need simulated data. Yeah. And then if you take the whole region where you might be able to operate, you're going to see it's a very small region where you're allowed to operate. Is that clear?
Yeah.
Yeah.
So in these machine learning techniques, how do you deal with the invariant systems? Is it related to what he asked? Like systems that are evolving over time, so you retrain your neural net every now and then, or is it robust to changes, or?
Depends on, this depends on, you're talking about time variant systems, right? Not invariant.
Yep.
Yeah, sometimes you have to retrain, sometimes you maybe have to train different neural networks for different hours of the day or whatever. Depending on I don't think there's a specific answer to that, or at least I don't.
No,
Yeah.
I'm just wondering how you deal with these time invariant systems.
It's, I don't think there's a straightforward answer that you do that and this can solve your problem. But maybe you have to have an ensemble of different neural networks, for example. Or if you want to go machine learning, because you can also go analytical, right? Or let's say first principles. Moving on.
Just a comment.
Please.
Is that kind of in line with, like all models, there is a difference between interpolation versus extrapolation? Because you can interpret between the known values that you've tested on and trained and tested on, but you go outside of that. Well, that's in the extrapolation world where you now have anything. Well, not anything can happen, but you have to have less confidence because you haven't trained or tested against it.
So your question is if it's because the lack of data, let's say in the safe region versus the unsafe, if it is because of interpolation versus extrapolation. So the thing is that what we try to do is we generate a lot of data on the boundary, right? So if you think about that, then just because we're on the boundary, I must be able to interpolate for the safe region, right? And I must be able to, then all the rest, I'm going to be saying that it's unsafe. It's kind of an extrapolation or, yeah. But the thing is, we cannot really identify well the safe region because we don't have a lot of data in there. So the neural network cannot really interpolate. That's what we see if there's not enough data inside the safe region. Because it gets so much overwhelmed from the unsafe data that then when we test accuracy, then yeah, the neural network is fine if it's 99.9 or 99.8. But the difference is, I'm going to have an example, so I'm going to explain that more in detail. Any other question? Okay, let's go then and we're going actually to go into more detail in what we discussed right now. Okay, but I'm going to spend a few slides before we go there. Training a neural network, okay? Basic principles. So just an overview, because we're going to talk a bit, or I mean also in your hands-on assignment or exercise, there's going to be decision trees and neural networks, right? So what these two things are, right? Decision trees are actually decision rules. It's an if-then statement, right? If my line flow is above a certain threshold, do this. Let's say the intelligence in the decision tree is which question am I going to ask first? So which line, for example, am I going to ask first? And what is the threshold I'm going to set? This is what the decision trees training algorithms are actually trying to figure out. The neural network is a bit more, let's say, sophisticated in the sense that I take the input and I have a linear weight here. So I modify this input in some sense. I multiply it with something. And then I have a nonlinear activation function here. And we're going to discuss about about specific one, this ReLU activation function, but this is just a max operator. So what happens here is, for example, I have my whatever input it can be, let's say line flow, I multiply it with something, and then I check if it is negative, then please output here 0. If it's positive, then output exactly the same value that you got as an input. Okay. That's what ReLU does. ReLU stands for rectifier linear unit. It's a max operator. So you get the max of 0. So if it's negative, then you're only going to get 0. And the linear weight that I have multiplied here, plus a bias. So this is a constant term that its edge can have. Okay. So it's a bit more sophisticated. But the idea behind it, to be honest, or the main principles are similar. Okay. About training, I'm going to talk about 3 major points. Because I don't know if some of you, I'm pretty sure you have trained before neural networks or decision trees. Some of you might not. So I just want to clarify what the batch size is, what the iteration is, and what an epoch is, because this is something that you are going to see when you train. I also want to talk a bit about what a loss function is, because I'm going to use that also later, but also because it's important. So all these are decisions you have to make. What kind of loss functions you're going to have. How big your batch size is going to be, right? I mean, now the modern toolboxes, they actually do that, all this for you. But at least the loss function, you can still experiment with different things. And then I'm going to also discuss this evaluation of performance that I think is very important. Okay, so to do that, instead of talking about neural networks, I'm going to talk about linear regression. Because if you understand how linear regression works, then neural networks is very similar. So let's suppose now that we have a set of data, right? And I want to estimate the trend line, right? I want to estimate a line that has a minimum distance from all this data. So what I really want to do is I want to estimate this weights W1, W2. Neural network training, again, we estimate all these weights. That's what the training does, right? So ideally, we want to enter all our data in the same, let's say, algorithm that's going to minimize the difference between this y hat that's going to be on the line and the y's that are actually the real data. Okay. Now, the problem is that the size of data is usually huge, so we cannot really have all the data at the same time in the training algorithm to have them optimized. So what we do is we split them into batches. Okay. Now, so this means that the total number of data is the batch size times the iterations. Okay. So for example, let's how many have here? If I have 1,000 data points and a batch size of 200, then this means I need to do 5 iterations because I need to get the first 200 in, then the second 200, then the third 100. What's an epoch? So here's the problem now, right? So ideally, I wanted all these 1,000 data points to put them all together in my algorithm and then minimize the distance for all these 1,000 data points together. But now I just do it over 200. And then I continuously adapt the weights. This is not going to give me the optimal solution necessarily, right? So what I need to do then is I need to do epochs. Epochs means that I pass the whole data set more than once. So one epoch is when I have all 5 batches run through the training algorithm once, and then I run that for several epochs in order to arrive at a higher accuracy. Questions?
So what it means is that, so you from one epoch to another one, you take your weights, or?
Yes, you always keep the same weights and you try to improve on them.
And then for the batch, the 5 batches, every time you have randomly assigned data points to each batch, or no, it's
in
the
every
same?
epoch.
Yeah, from one epoch to another.
Yeah, this depends on what the algorithm does underneath, and there are different approaches. Yeah.
If it's a linear regression, then you get the same answer each time, right? So this is only doing these multiple epochs is it's to address the nonlinearity.
Yes, yes. Because the neural networks are nonlinear because it has a nonlinear activation function, but also the problem is not so simple as just yeah, absolutely, yes. But thanks for this point. Maybe I should adjust my example. Other questions?
So I'm relatively new to neural networks. Can you explain the logic behind how you might choose a batch size?
I'm not sure in the sense that depends on your problem. You just have to try some sizes and see what works.
Does it depend on compute power?
It could, yes.
Because if you have infinite compute, then you just all work together, right?
Yeah, but the problem soon will become intractable, of course. Yeah. But then the question is also, can you parallelize or not, and how are you going to share the information? It's a parameter that you have to set. You can trust TensorFlow, whatever, to set this parameter for you, or you can experiment with different sizes. 200 is very small. We're talking about thousands of data points per batch. That's what I can say, but more than that, this depends a lot on your problem. And other questions?
I think from MATLAB Toolbox, I remember you never set the number of batches. So there should be some sort of maybe intelligence behind it, so they decide how many batches they should have, or?
Yes, there is. So there are some default values where they decide how big this should be, but we can always change this number if you want. But absolutely, yeah. So you let the algorithm do what it knows to do best. Yeah.
Each time you do an epoch, do you select a different sample for each batch?
Yeah, you reshuffle.
Yeah, you randomize it. Yeah.
Yes.
Okay.
Okay. Moving on. Or any other questions? Next point, loss function. Okay. As I mentioned, we need to define an objective function that's going we need to minimize a function, and this function must actually represent the distance of the points on the line, that's our estimates, based on the real point. And there are many different loss functions one can pick from. So what we try to do is minimize the distance between y and y hat. This is my estimate, this is my real value, subject to that y hat is actually on that line, right? So I only actually need to minimize that. So there are different options. I have here a couple of examples that you can look at. What we're going to discuss here is the cross entropy. It's a very common loss function used a lot for binary classification, and binary classification for us means safe or unsafe for an operating point. So that's what we use. So here's now the thing. My real data are discrete values 0 and 1. 0 unsafe, 1 safe. Or let's assume that it's like that. My estimated data are continuous, or the output, let's say, the estimate output, is continuous between 0 and 1. So what I'm trying to do is minimize the difference, and I'm using this function, and some insights on that. The first is, as we already discussed, we minimize over all points on the batch, right? So it's from I equal to 1 up to n. So this for all points inside the batch, we try to minimize this function, number one. Number 2, as I said, the actual values are discrete while the estimate values are continuous. Number 3, why the minus? One said convexity. So I didn't, please, one. Who?
0, 0 to 1, you always get a negative log, so it makes the information positive.
Correct. Okay. So let's take a better look at it. So my y is going to be either 0 or 1. So if it's 0 or 1, so this means one of these two terms is going to be 0. It's going to be out of the equation, right? So we only focus on the other one. So let's focus now, just for the sake of example, here. So let's suppose that this is 1. Now, my logarithm, because this is between 0 and 1, this is going to be negative. The logarithm of something between 0 and 1 is going to be negative. And I want my loss functions to be, by definition, always positive. Okay? Because I want to minimize a positive value. I want to bring it as small as possible. And that's why we add the minus. Okay? Inside number 4, so how this looks, actually this must have been, I think, down to 1. But so this is how it looks. So if it is, so let's assume now that my actual value is 1, right? You see that if my estimate value goes close to 0, this goes like a barrier function. I mean, for the ones familiar with optimization, it's like a barrier function. So this means that it really increases dramatically the more we deviate from the, if the estimate value deviates a lot from the actual value. That's the impact of the load. Okay, so these are some insights how this cross entropy loss function works. In the hands-on, you are going to have the cross entropy. It's good to know how this works. You can also experiment with different loss functions if you want. Questions? Okay. Next point. Next point is confusion matrix. And I mean, current tools, actually, they produce this. So it's good that you are familiar with what a confusion matrix is. So it's a 4x4 matrix, if it's binary classification, right? So the one is the actual values, and this is what my neural network or whatever decision tree tells me it is, right? So true positive is what I really want, and true negative is what I really want. This means that my estimate or my prediction and the actual one are the same. And then we have also false positives and false negatives. It's straightforward, I think, but try to remember that because we're going to use it a lot for the next 2 slides. Okay. So for me, this means that actually safe and predict safe is true positive, actually unsafe, but it was predict safe is false positive and things like that. Okay. Now, this is where I want to arrive, and this is the discussion we had. So the most common metric for the assessment of decision trees or neural networks or maybe also other approaches is accuracy. And I have over there actually the confusion matrix still, so if you forget about it, then you can always look up there. So accuracy is the ratio or the proportion of the true positive and true negative, so these are the correct predictions, compared to the total size of my test database. Okay? That's what it is. How much is the accuracy here? 95%. How's that? What? 95%. Yeah. So it's exactly 480 plus 470 over 1,000. So this is actually, I'm missing 50 here. It's 50 over 1,000. Yeah, 95%. Okay. The point I want to make is that evaluating accuracy only is not enough. Okay. So let's take, yeah, please go ahead.
What about if you're classifying between can my model predict a rare disease or not, where you're going to get a lot of distortion? You know, you'd rather, getting one false positive is very different to getting one type.
Yes.
Your type 1 and type 2 errors really play a role.
Discuss about that.
Okay.
Just, yeah, if you, 1 or 2 slides and then we'll give it back. Let's see this example now. How much is the accuracy here? Who said that? Yeah. It's 95.1. What's different here? Okay. Yeah. Exactly. Exactly. Okay. A random guess will get 98. It's highly unbalanced. This is a bad test database. I have seen submitted paper that I reviewed, having this kind of test database and claiming that they do 98%. So be aware of what unbalanced data sets can bring to you. Okay? And okay, yeah. As I said, it's difficult to get a balanced data set in power systems if we could go about security, right? But you have to be aware that you have to have a balanced data set to make sure that you get meaningful results. Yeah?
So if the you have 50% 0, 50% 1, and what you don't know what your test would look like. So when you test it on a predefined test set, that's one thing. The other thing is when you test it, like when you implement the tool that you developed and it's seeing new data. You trained it on 50-50 data set and test it on 50-50 data set. What if the data that is coming is different in nature? For example, it's not 50-50 chance that it's stable or not. So what if it's like 90% stable, 10% unstable?
That's going to be fine as long as your test data set reflects this data that's coming to you in reality. So then, after that, it's not a problem anymore if I have a lot of safe or unsafe data in reality when I let it run, right? When I deploy it, it's fine. Whatever comes, it's fine. The question is if this test data set reflects the real data you're going to get when you deploy it.
But doesn't it affect the feature space? When you force it to be 50-50, you're already putting a specific feature space into account. Like you already are considering that feature space would look like something. But then,
no, because so okay. First of all, I have here two things. The first is I have here the 50-50. I'm not saying that it must be 50-50, but it must definitely be balanced. So it can be 40-60 or 30-70, I don't know, but it can be balanced. One more thing is that so this is my whole space, right? And this is my safety space, right? What I'm saying is if I have 500 here, I must also have a large number here to make sure that it's trained well. I'm not saying that it must be necessarily 50-50, but definitely not like that. I cannot have 20 points that are safe and 980. That's not. Okay.
Otherwise, it would only produce one.
Yeah. So you must make an effort to produce a lot inside that, even if it's a math. So if you take this kind of uniform sampling, it's going to give you 2% in there and 98% there. And you must go away from the uniform sampling and go to a more direct sampling that is going to give you many more inside the safe space. Okay.
So isn't there an equation for unbalanced data accuracy, which is a linear disaggregation of the accuracy formula here, that is like TP divided by TP plus FP plus TN divided by TN plus FN divided by 2, which is an average.
I don't think it gives you the same result.
Yeah, it will be different results, and it's good for unbalanced data.
Yeah, I'm coming back. Actually, that's exactly the next slide, because this answers both questions. And I'm going directly to the next slide. And that's the one, okay. So accuracy is not on, yeah. So we have recall, I think that's what you said, and specificity. Or I don't know, maybe you said precision, maybe. You said, as long as you do a statistical analysis of this performance, you have to take into account all these metrics or several of those, okay? And so in a paper that we published in Partech this year, we actually came up, or I think also other, I don't know, but we haven't seen that before, to be honest, this kind of spider web diagram. And then the different, so then depends, for example, if your false negative is very important, then, for example, I don't know who's going to be. The specificity is very important to you. So you are going to look into a setup for a neural network that's going to have high specificity. So accuracy is not enough, especially for unbalanced data sets. You need something like that. And then you need to assess. So if you see here, these are deep neural networks, but with different, let's say, different layers, different number of layers, and different number of nodes. And there's no single one that performs well, I think, in everything. Okay, you win some, you lose some. So then it's your decision to pick whatever you think is going to be good for you. But reporting only the accuracy is not enough. Okay, that's the main point. Good. I only want to talk a bit about this MCC, multi-correlation coefficient. This actually gives a pretty nice output in a way that if this MCC is 1, then the prediction is actually perfect, which means that everything is predicted correctly. If it's a 0, it's like flipping a coin. Okay? So you can have a very high, you have had cases, very high accuracy, but this MCC was around 0, which means that if I give it to the neural network, or if I just flip a coin and decide if this is safe or not safe, it's going to give me the same probability result. Right? So I found this metric very helpful to see if it makes sense to have a neural network decision tree or whatever for that. Okay. Of course.
The decision is 50-50%? The correctness of the decision is 50% if MCC is equal to 0?
Yes. So it gives you 50% probability to have the correct result. And then instead of spending all this time training a network, then you can just flip a coin. It's going to give you the same. Okay. Good. One last thing about training. When you implement things, at least so there are several tricks. Some of them, the toolbox now do it themselves, some of them not. So what we have found very helpful, and I just want to mention that, is first of all regularization. Power systems do that already. I mean, participation factors, if you are familiar with stability, is something like that. It's like normalization. So I have many different variables that have many different scales. So bring everything from 0 to 1, regularize. And the second is, especially for classification, this is very helpful. So up to now, have actually talked about safe and unsafe. It's one scalar. If it's 0, it is safe. If it is 1, if it's 0, it's unsafe. If it's 1, it's safe. Okay. From now on, we're going to talk about a vector with two elements, y1 and y2. Okay. So if it is safe, it's going to be 1, 0. If it's unsafe, it's going to be 0, 1. And then we're going to see, because the neural network is going to be continuous, if y1 is larger than y2 is safe. If y2 is larger than y1 is unsafe. Okay. This helps in the performance of the neural network. Questions about this? Yeah.
So my question is about regularization.
Yeah.
Is it a proven theory, or it's just by trial and error? And see it's working.
No, but I mean, if you also read different tips and tricks, this is something that, and it makes sense, okay? Yeah. Because if you have variables that one is from 0 to 10 and the other is from, let's say, 0 to 1,000, then these weights are going to have to address them differently. Optimization does exactly the same inside the optimization algorithm. They all normalize to make sure that they have the same range.
Computer precision plays a role here as well. One of them is,
Absolutely right, yes. Any other questions? Great. Takeaways. We need a balanced training database. Okay, number 1. Number 2, accuracy is not sufficient as the only metric. You need something more than that. And number 3 is that sometimes you can boost performance by doing some simple tricks. Don't just take your problem, fit it in there, and then see what you get. Okay. Be smart about it. And that's not only for neural networks, it's the same for optimization and for many other problems, right? We cannot look at something like a black box. We must help the algorithm to help us, after all. Okay. So learn what are the major points of how you can help this training process. It can make things much faster, much better. Good. Yeah.
One more. Yeah. So you say accuracy is not sufficient, and I understand it for a binary case. But if you're doing, for instance, load prediction, what else do you need other than accuracy to make sure that you trained a good model?
Yeah, I think for regression, accuracy is definitely much more central.
There's many metrics for accuracy with regression. There's bias, variance. Yeah.
Okay. Yeah. Very good. Thanks for the comment.
You said there are other measures.
Yes.
Yeah. Oh, okay. Oh, okay. Okay.
Yeah. Moving on. Any other questions? And we're done with that. We'll do that, and then the next hour we'll do. Now it's more a bit about insights and applications. As I said, data is very important. Okay. And because data is very important, we started looking a bit into that. So I'm going to discuss a little bit about our experiences with that. And the main motivation behind this work is that, as we said, historical data is insufficient. They are limited in a very small area because power systems are operated conservatively. We need simulation data. And if we need simulation data, the question is, how do we generate a high quality or a good quality database? And if you start thinking about it, then you're going to realize that's an extremely complex problem. So we tried to come up with an algorithm which we wanted to accommodate, and it can accommodate numerous definitions of power system security. So n-1, n-k, small signal, transient, the framework, right? What we have created the data set is for n-1 security. So, okay, first of all steady state, like all component limits, okay? But then plus n-1 and small signal, okay? And we have this for the 14 bus system and the 162. The 14 bus, you're going to get it with the hands-on exercise. The other is available here. And we have created an algorithm that, at least based on our computations, it's 10 to 20 times faster than any state-of-the-art algorithm. And the main idea behind that is because is what I like to call sampling beyond statistics, okay? Up to now, all these database generation methods were based on sampling, and sampling was based on statistical methods, which makes sense for many other fields. But in power systems, we have so much information through the models, right? So why not exploit this information and just do not random, but just do sampling or statistical sampling, okay? Okay, so here's what we want to do, as I have already been discussed. This is the unsafe space, the white space. This is a real representation, 2D projection of the 14 bus system, okay? So this is the unsafe space, or the white. The blue is the safe space. You see that's non-convex, right? And the gray region is where we want to focus, is what we call the high information content. This is the security boundary. So our idea was that if we generate a lot of points around the security region, around the security boundary, then we have mapped the security region, and then we're good, right? Then we figured out that probably we need also to start populating the inside and outside as well. But yeah. So how do we do that? Using convex relaxations and direct walks. And I'm going to explain how we do it, okay? Let's start. This is only steady state, okay? Because the first thing for any safe operating point is that it must be safe or inside the feasible region here for the components, okay? So what we do is we use insights, or if you want, certificates, because it's really about certificate from the convex relaxations. So the convex relaxation is like an envelope, right, around the non-convex stable region. And now the certificate says the following, that if an operating point is infeasible to the convex relaxation, it's going to be infeasible to the true feasible region, okay? Clear? So we can talk a bit about OPF, right? So this is the feasible region of the OPF. So this is all the points that the OPF must pick the optimal, right? The convex relaxation relaxes the problem and creates a convex feasible region around it. So by definition, the relaxation will be an area that is convex and includes the whole convex region. Okay. Now, if this point is outside this region, means that it violates some of the limits of the convex OPF, right? So if it violates limits of the convex OPF, it will violate definitely the limits of the, right? Okay. Now, what I'm trying to do now is I'm setting up an optimization problem saying that I want to minimize the distance from this point that I'm going to satisfy the constraints of the convex OPF. Okay. So these are the distances. And we have two versions of that algorithm, and one then improved it. So in the first version, we created the hypersphere. So here it's just circles. So now we have this as a center, this as a radius. This whole area is definitely unsafe. This way, we can actually quickly classify unsafe regions and discard the safe regions. But the cool thing with that is, at least for the outside, is that because this is convex, now I can populate it very easily. It's a convex region. I can just take some points inside there, and then I know that all these are going to be unsafe. Oop. This is a 14-pass system, so this is actually the paper that describes all this. This is a real representation in 3D. It's again a projection, right? Because this is a 5-dimensional system, and the 162 bus is much more. So these are the different parts of these spheres that we're discussing about. And now recently we have a new paper that instead of the hypersphere or the sphere here, we're talking about hyperplanes. So if I draw this line here, I can get a tangent, and then I can discard the whole plane. It's much faster. And let's stop here.